This area of volume stuff that we're doing is so very important because it typically spans Calculus 1 and Calculus 2 in college, so which means it could potentially be part of both of those classes. Depends on where you take it and how their pacing is going to be there. But what we're going to do, here's our steps for finding volume using the disk method. So this video, I'm just going to talk about where this formula comes from, and then we'll have these steps written down right there. And then the next video, I'll actually show you some examples and I'll work out some of the problems right there. So just make sure you get these steps down, get that formula down. Here's what we're doing the next couple of sections there. We're going to take a curve and we're going to rotate it around an axis of revolution, right? So if I take this line and I rotate that, let's say I rotate it around the y-axis, all right? So that little like refresh icon, little loopy symbol there, that indicates the axis of revolution. I'm going to ask that when you draw your bounded area, make sure you indicate what your axis of revolution is there. So if we have any questions, then I gotta get my mind right about what your axis of revolution is, because that's gonna make a difference to what this capital R and the little r is going to be on this disk method, right? But here's what we're doing. If I take this shape, this bounded area, and I revolve that around the y-axis. Maybe you see the shape there, maybe you don't there, but I'm hoping that you see that there's gonna be a cone there. And if it's a cone, I can use a geometry formula to find the volume of that cone. And then notice here though, if I take this same shape and I make the x-axis my axis of revolution, so I take this shape and I revolve it around the x-axis, we're still gonna have a cone there, but to me that looks like a different cone. So that axis of revolution definitely makes a difference. Sometimes you're going to get a completely different shape depending on what that axis of revolution is there. So when we draw our bounded area, we'll make sure we indicate that axis of revolution. But see, if that's just a linear function, I can technically use a geometry formula for a cone is at 1/3 pi r squared h, and I can find that volume right there. But here's where we're going to start to need the calculus right here, the calculus technique. If I take this bounded area and I take this and I revolve it around the x-axis. So I just take that area and I revolve around the x-axis, create a three-dimensional shape. It looks like we're going to get a sphere, like a ball, like a basketball or something like that. And if it is spherical, then I can go ahead and use like a geometry formula for that. But see, now look, if I make my axis of revolution now the y-axis, so I'm going to take this same shape and revolve around the y-axis. That is not a basketball anymore. That's a completely different shape, right? And so I'm not sure what you're visualizing there. Some of you might see like a gelatin mold. Some of you might see like a little bundt cake, like those little templates where you make a bundt cake or something like that, or just like a tunnel, you know, or half of a bagel or something like that, right? The top half, you know, put that cream cheese up on there, some peanut butter, something like that. But anyways, so the thing is, like, we don't have a geometry formula to find the volume of like a gelatin mold or a bundt cake template thing or something like that, right? So we're going to need the calculus in order to find that volume. Okay, if we take this here, this is like y equals square root of x graph. If we take this shape and we revolve it around the x-axis, all right, I'm not sure what you're seeing there, like maybe like a tumbler or a little glass or a little chalice. If you're a Tom and Jerry fan, you see like a ham or something. Like there's like, I see like a ham where like, you know, just from watching those cartoon stuff there. So the good news is if you're having trouble seeing what these pictures are, the way I'm going to give you these steps and the way I'm going to give you the nuts and bolts part of these problems, whether you can visualize it or not, okay, I'm going to show you a way you can do this where you're going to find the volume of the actual shape there, okay? So I remember when I learned this stuff in college, there's something called a disk in washer method, but the washer method, if it has a hole in the graph, and so I had to visualize and really see what that stuff was going to be. And then if I couldn't visualize, I had a tough time doing that when I first learned this stuff. And I wish I would have had these more systematic steps where I could have still found that volume right there. Because sometimes if you didn't see the picture the right way and I chose the wrong technique, and then I was screwed, right? So I'm just going to give you an easy way to do these without even seeing the pictures. But it's kind of nice if you kind of see what that picture is going to be. Now, you might be thinking, why did you draw the same graph twice? I'm not losing my mind. I'm not crazy. I drew the same graph twice because I want to show with you. Let's say our axis of revolution is this like y equals -2 line. So I'm going to take this same bounded area and I'm going to revolve that around that axis of revolution like a chicken out of rotisserie. You know, you cooking that dinner meal right there. So the thing is, if you look at that picture when you revolve around the x-axis, I'm seeing kind of like a similar thing, but it looks like there's going to be a giant hole in the middle of this thing. So what I'm kind of pretending this is like one of those like chip dip bowls where you have like the plate around the outside, and in the middle of that you have like a little container for that you can put like the dip in, and you got the chips on the outside and you got the dip on the inside. You know, the salsa, the con queso. But So that's what I'm kind of seeing right there. And so what we're going to learn is techniques. So we're going to create these shapes, working with these graphs, these three-dimensional shapes, and we're going to find volumes of these shapes. And there's about 3 techniques to find the volumes. There's disk method, shell method, and then also the cross-section method right there. Now, technically, this is the disk method for all of these, but when you got a hole in there, it's technically called a washer method. I'm just going to show us just the disk method, and it includes the washer technique there. It'll include the steps here, will help us out whether there's a hole in that shape or whether there's not a hole in that shape right there. You don't necessarily have to visualize the shape, but what you can do is find the volume of that shape. So depending on where your visualization skills are at there, you don't necessarily have to see the shape in order to get all these right. And then what's just kind of interesting, there's just a nice little picture in an old book that I had right there where like the graph starts off like this, right? Because all of the problems we're going to do are going to be around the x-axis or the y-axis, or like the y equals -2 line or y equals 2 line. And we're going to have these different graphs and these different curves and these different axes of revolutions, right? And so when you do that, you know, notice what this is asking. This is asking us to find the area that we did for the top curve minus the bottom curve, or right curve minus the left curve. And it's talking about volumes and stuff there. And then notice what it turns into is like this ended up being like the actual Hoover Dam, like a model for that Hoover Dam, and then they kind of use that model to figure out what the amount of concrete that they should use or whatever material they use to kind of build that thing right there. So I mean, we're going to be doing a lot of volumes and shapes around the x and y axis and the different axis revolutions there, but it can turn into some different things there. Now, if you're interested to where this formula is coming from, okay, the reason we use the disk method, all right, look at this shape that I got here, all right? If I want to find the volume of the shape, what I got is just tons of these circular discs. All right, so if I wanted to find the volume of this shape right there, what I could do is find the volume of each one of these circular discs and add up all those volumes, okay? And you know the integral is an accumulator. The integral will add that stuff up for us. Just like when we first learned area in a couple chapters ago, how we did slam like an infinite amount of rectangles in that space to find the exact area. Now you might be wondering, what's this capital R? What's this little r? All right, so the capital R, if I take one of these circular discs, all right, the capital R is the radius of the bigger circle, all right? So like sometimes your shape will have a hole in it, sometimes it won't, okay? And so you got this bigger circle and then you got that little circle for your hole. So the capital R is the radius for that big thing. So from the center to that farther edge of that disc right there, right? So you got that farther edge, that's your capital R. And so if I do pi times that capital R squared, it gives me the area of this whole entire face, including that hole, like that donut filled in. And then the little r is the radius of the actual hole, that little circle right there. And so if you have a hole in the thing, if the radius is equal to that, we want to subtract that out. And so if we do pi times the capital R squared, gives me the area of this whole thing. Pi times that little r squared gives me the area of the hole if there's a hole in the graph. And so when I subtract that out, it'll give me just the area of this outside piece, right? And so that's just areas. And then you're going to add up a bunch of areas, right? And so pi times r squared times pi times r squared. So you're going to add up a bunch of areas. And so if you just do that, remember what the integral is going to do, because right now, if I run my finger on there, if these are sharp edges, it's like, oh man, I'm going to cut my finger or something like that. But we know what the integral does. It's going to put an infinite amount of like circular disc in that area, and it's going to act like the sandpaper, just smooth that out for us and give us the exact area. And then here's the deal. So you're thinking, okay, I thought we were doing volume, not area. The dx or the dy, that's what turns it into the actual volume, okay? So the dx or dy, so we're going to find the area of this shape, and then the dx or dy, this disc has a width to it. That's your dx or your dy. So when you're times it by this dx or dy, that's like that added little height or that width of that actual disc, and that's what turns it into the volume right there. So if you do like the area times the height, then, or times that width right there, that depth part right there, that's going to give you the actual volume, and your integral is going to add up a bunch of those. And so that's what the disk method is doing. That's where that formula is going to come from right there. So I just wanted to kind of have a video for that, but here's our steps. We're going to draw our bounded area on all of these, and then you can label your axis of revolution there, kind of get a couple numbers on the graph there. Use your graphing calculator if you need to get the graph, that's fine, but make sure you just jot that down on your paper. We got to see the graph down on your paper. And then we're going to draw a rectangle perpendicular to the axis of revolution. And then that rectangle is going to represent like one of those circular discs that I just got done showing you. And the dx or dy, I will stay consistent every volume technique that we're learning here, the dx or dy is determined by the width of the rectangle. So the width of the rectangle is the little part. So if you draw your rectangle up and down, then the little part's horizontal, like the x-axis is horizontal. That's how I remember it's a dx prime. If you draw your rectangle like this way, sideways, then that little part, that's the width, that's vertical, which is like the y-axis, which is a dy prime. Learn it like this, all right? Sometimes people have misconceptions when they do this section of homework, they'll think, oh, this is always a dx prime or this is always a dy prime. That's not always going to be true. It might be true for this method, but then you have to learn a separate set of rules for the other method that I'm showing you. If you learn it like this, I will keep this consistent when we do our shell method, when we do our process stuff there. So we're going to stay consistent with that. So just learn that. And I just got a great way teaching this stuff there. If you do what I asked you to do and then just keep working at it, we're going to become experts at this stuff. And then that's what we talked about. The capital R is the distance from the X revolution to the farther edge. The little r is the distance from the X revolution to the closer edge of your bounded area. So I'll go through the nuts and the bolts of how to actually go through those steps and how to work out some examples in the next video.